Welcome everybody to episode 11 of the Quantum Science Seminar. Today is all going to be about quantum nanophotonics. As always, please ask questions. If you have questions, please send them to quantumscienceseminar@gmail.com via email, or use the YouTube live chat at the right or at the bottom of your screen. We are going to take a break about halfway through the talk and ask the first of your questions, if there are any, and answer the rest of your questions at the end. Our speaker today has also kindly agreed to answer all of your questions. So if there is way more questions than we can answer, which is usually the case, then these questions will be posted later on our website. Please also note there's a 30-second time delay between what you see and what we see. And with this, I will hand over to Ofer, who will introduce our speaker today.
Thank you, Sebastian. Good afternoon, everyone. It's a great pleasure for me to introduce today's speaker, Professor Arno Reuschenbeutel. Arno Reuschenbeutel is an Alexander von Humboldt professor in the Humboldt University of Berlin. He did his PhD under supervision of Nobel laureate Serge Haroche and held professorship positions in Mainz, in Bonn, and for 10 years in Vienna. Arno is a world leader in the quantum optical interface between atoms and nanophotonics, in particular nanofibers, about which we're going to hear today. He has received many awards, including the 2006 European Young Investigator Award of the European Science Foundation, and recently the Alexander von Humboldt Award. So without further ado, it is a pleasure to host Professor Rauschenbeutel today, who will talk about revisiting light-matter interaction in quantum nanophotonics. Arno, thank you for coming. The stage is yours.
Okay, thank you very much, Ofer, for the kind introduction, and also thank you for inviting me to give a seminar here. It's a great pleasure and honor. As Ofer said, we would like to explain in this talk how in quantum nanophotonics, so when emitters are coupled to nanophotonic components, light-matter interaction is altered and may exhibit surprising effects. Okay, so to start, maybe as an introduction, let me recall that the optical components that you use may be much larger than the optical wavelengths, like, for example, lenses or prisms. And in this case, geometrical optics is usually the theory that describes everything that we do and see. If our components now get smaller or have features that are on the size of the wavelength, then diffraction and interference has to be taken into account. And in this case, usually it's still enough to use a scalar wave theory in order to capture these effects. But what we will look at in this talk now is the case where our components or emitters are much smaller than the optical wavelength, or on the order of the wavelength. And it turns out that in this case, for some of the effects that occur, we have to actually use a full vectorial theory to understand what is actually going on. So let me come to the outline of this talk then. So the first part of the talk will be on the interaction of atoms and nanophotonic emitters, nanoplasmonic emitters with a nanophotonic waveguide. So this is a optical nanofiber, a silica waveguide with a diameter smaller than the wavelength of the guided light. And what we will see is that in these interfaces between emitters and nanofibers, an effect takes place which makes the coupling of the emitters to the light in the fiber propagation direction dependent, or another word for that is chiral interaction. I will then show you that these effects even prevail in free space. So even when looking at an emitter in free space, you can have propagation direction dependent interaction with the light fields, and this leads to an effect where we see a single atom at an apparent position which differs from the real position of the atom. And then finally, in the last part of the talk, I will consider the interaction of an ensemble of emitters that is coupled to a nanophotonic waveguide, and we will see that a very strong nonlinearity can arise for the light that interacts with these emitters, even though each single emitter is only weakly coupled to the guided mode. So with this, I would like to first introduce the properties of the guided modes in optical nanofibers. So as I said, these are cylindrical dielectric waveguides with a diameter that is on less than the wavelength of the guided light, say 300 nanometers diameter, okay? And for these waveguides, then a significant part of the optical power is guided outside of the waveguide in the form of an evanescent wave. So when we plot the electric field, then it still peaks at the center of the waveguide, but outside of the waveguide, there is a more or less exponentially decaying tail of the electric field, okay? And now the field outside of this waveguide, of course, has to fulfill Maxwell's equations, and in particular, it has to fulfill Gauss' law. That means that the divergence of the electric field outside of this waveguide here has to vanish. And if we now apply Gauss' law to a mode that is propagating along the z-axis, such that it's actually amplitude of the field which depends on the transverse coordinates x and y, and there's a phase factor because of the propagation along z, then we see that actually there is a longitudinal component that occurs in the evanescent field, provided that the transverse divergence does not vanish. So the longitudinal component is a component of the electric field that oscillates along the waveguide axis. Now let us consider, for example, that we launch a linearly polarized light field into this waveguide. And we look now at the polarization state just above and below our nanofiber. And for symmetry reasons, of course, there is no X component of the electric field. So what we see is that in addition to the Y component of the field that was also initially there for the light that we coupled into our nanofiber, longitudinal component appears, which is proportional to the gradient of our electric field along the y-axis here. And this, of course, gradient, as we see here, changes sign on either side of the fiber. So once it's positive, once it's negative, which means that the sign of the longitudinal component here changes above and below our waveguide. In addition, there is this phase factor of I between the longitudinal component and the transverse component, which means that the two components oscillate in phase quadrature, 90 degrees out of phase. So their interference then gives rise to elliptical polarization, or for simplicity, let us just say circular polarization above and below the waveguide. But this circular polarization is different from the circular polarization that you encounter for paraxial light fields. For a paraxial light field, when we talk about circular polarization, the electric field behaves like the propeller of an airplane. Here, the electric field behaves rather like the rotor of a helicopter. It turns in the plane that contains the direction of propagation. And what we see is that the change of sign of the longitudinal component above and below the waveguide then leads to the light turning, say, clockwise above the waveguide and counterclockwise below the waveguide. We can characterize these polarization states by a so-called ellipticity vector. This is a vector which is normal to the plane of polarization, and it's unity for circular polarization and plus and minus, one for sigma plus and sigma minus. And for a linear light, it would, for example, be 0. So in this case, this ellipticity vector would point into the screen above the waveguide and out of the screen below the waveguide. And it turns out that this ellipticity vector is also the same as the spin of the light field, where here spin is not a quantum mechanical property or quantity. It's actually the classical intrinsic angular momentum carried by the light field. Okay, and what we see is that the sign of this transverse spin, which is transverse to the direction of propagation, depends on the transverse position. So it changes sign above and below the waveguide. And this effect then is referred to as spin-orbit coupling of light. And then there is another effect, because if we now assume that the light, rather than being launched from the right into the waveguide, we launch it from the left, then it's like running the initial movie backwards, meaning that the electric field vector will spin counterclockwise above the waveguide and clockwise below the waveguide. And then this means that actually the local spin changes sign with the propagation direction. And this effect is referred to as spin momentum locking of light. So the spin of the light is no longer an independent quantity, but it is one-to-one mapped on the wave vector of the light. If we flip the wave vector, we also change the sign of the transverse spin. And this spin momentum locking of light then has an effect on the spontaneous emission if we place an emitter onto our nanofiber. For that, let us assume that we have some, say, for example, nanoplasmonic emitter on our nanofiber, and that we suitably optically excite it such that it emits circularly polarized light, where it is circularly polarized in the plane containing the fiber axis. Then, following what I explained you, the only optical mode that can actually support this polarization at the position of the emitter is a left propagating mode. So this emitter will, the part of the light that it couples into the waveguide will travel to the left rather than to the right. And of course, if we now change the polarization, so if we change from clockwise to counterclockwise rotating electric field, then it will emit to the right into the waveguide. That means that the polarization of the emitted light defines the direction of emission. And this effect is referred to as chiral coupling. And I would like to stress that chiral coupling does not only occur in our nanophotonic platform, it has been observed in a number of other works, so you can check out the experiments by these co-workers, or these colleagues here. So now coming to the actual experimental setup, it consists of a silica nanofiber with a diameter of 300 nanometers, and then we place a gold nanoparticle with about 100 nanometer diameter onto the fiber. And we can set the polarization of the light emitted by this nanoparticle by just exciting it with an external laser beam that now hits the plasmon resonance of this nanoparticle. And the dipole that is induced by our excitation laser is just a carbon copy of the local polarization of the excitation light at the position of the emitter. Okay, and this polarization can be set simply by using a quarter wave plate here. So initially the laser is horizontally polarized, but then it goes through a quarter wave plate. We can change the wave plate angle and then record the photon flux emitted to the left or to the right, which is then recorded with two photon counters at the two ends of our fiber. And then we can define so-called directionality, which is just the difference between the right and left count rate normalized by their sum. So if we then have a directionality of +1, it would mean all light arrives on the right detector. If we have a directionality of -1, it would mean that all light arrives on the left detector. And if we now plot this quantity that we measured as a function of this wave plate angle theta here, then depending on whether the particle is above or below the nanofiber, we observe these two experimental signals here. So the dots are the experimental measurements of the directionality, and the line is a theoretical prediction. And for 45 degrees, the laser is circularly polarized just behind our wave plate. And for 90 degrees or 180 or 0 degrees, it's linearly polarized. And we see that we have a strong directionality, both for the nanoparticle above the nanofiber and for the nanoparticle below the nanofiber. The maximum directionality that we observed was 95% converted into photon fluxes, or the ratio of left-right photon fluxes. This means that we had a ratio of 40:1 of the photons emitted by the emitter into our waveguide, rather to the right than to the left. Okay. So here in this experiment, this is of course only classical nanophotonics, no quantum anywhere, because our emitter can just be seen as a small antenna that radiates light of polarization that can be chosen. It would, of course, be interesting now to study the same effect in the quantum regime. And this can be done by coupling laser-cooled cesium atoms to our nanofiber. I will go more into detail of how we actually place the atoms at a distance of about 200 nanometers from the nanofiber at a well-defined position later. For the moment, just take my word for it that this can be done. So we place a number of cesium atoms along our waveguide, and then from the outside excite them with a resonant laser on the D2 transition, and then look at the light spontaneously emitted by the cesium atoms into our waveguide with 2 detectors, and can again determine the directionality of the emission into the waveguide. Now, if you look at it and remember the experiment with the gold nanoparticle, this looks exactly the same. So you would maybe also expect exactly the same result. However, there is an important difference between cesium atoms and the gold nanoparticle, because cesium atoms are multi-level atoms, and thus they in general will not preserve the polarization of the light that they scatter. So that means that depending on the excited state that the atoms are excited to, they will emit light of different polarizations, and thus we will also expect different directionalities. For example, if we excite this outermost Zeeman substate of the excited state manifold, MF equals +5, then the atom has to emit a sigma plus polarized photon, and we expect strong directionality. If it is prepared in this outermost negative Zeeman substate -5, then it emits a sigma minus polarized photon, which means that we actually expect also maximum directionality, however, emission into the other direction. And for this more inner lying Zeeman substates, all 3 transitions are possible. So sigma plus, sigma minus, and pi, which means that here we expect a small directionality because we average between emission to the left, right, and just symmetric emission for pi polarization. So if we now plot the directionality as a function of the magnetic quantum number of this excited state here, then we indeed see the expected behavior. So here the red bars are the theoretical predictions for the directionality as a function of magnetic quantum number. And the data points are indicated by the circles here. And you see that here we also have a strong directionality in terms of ratio of photon fluxes. This was 10:1 of the light emitted to the right rather than to the left for this outermost Zeeman substate. And here I would like to stress that differently from the gold nanoparticle, which has just one polarization state and then emits either to the left or to the right or something symmetric, more symmetric. In this case, the directionality of the emission is controlled by the quantum state that we prepare. So in principle, of course, you can also now prepare the atom in a superposition of excited states, and then it would be in a superposition of emitting to the left and to the right. So rather than summing up and giving you perspectives on what this can be good for, I would like to just highlight a review article that we wrote together with the group of Peter Lodahl and with Peter Zoller's group in Nature, where we discuss these chiral effects in quantum optics and the perspectives that are opened by this direction-dependent coupling of light to nanophotonic structures. And before taking questions on this first part of the talk, I would now like to thank the people who actually did the experiments. This is Jan Petersen and Jürgen Volz for the nanoplasmonic emitter experiment, and for the cold atom experiment, it's Clément Serin, Bernhard Albrecht, Rudolf Mitsch, and Philipp Schneeweiß. And with this, maybe I take questions now, or how much time do I have? Or I just go through the next slides. I guess I just take the next topic and then take questions. That's maybe the better point. So what we saw is that here we had spin momentum locking of light at play in a nanophotonic component. And the question is, do we really need this nanophotonic component to observe effects of that kind? And it turns out that what was at the essence of spin momentum locking was a transverse gradient of our light field. So as soon as the transverse confinement of the light is comparable to the wavelength scale, we get the strong longitudinal components, which give rise to elliptical polarization that changes sense of ellipticity when I change the direction of propagation. And it turns out that this can also be observed in free space. This work was done in a collaboration together with Rainer Blatt's group at the University of Innsbruck. And before going into the experimental details, let me just briefly tell you how spin orbit coupling and spin momentum locking looks like in free space. For that, let us consider a linearly polarized focused Gaussian laser beam, which is linearly polarized in the plane of the screen. And then applying, as before, for our nanofiber guided light Gauss law, we see that again, we have longitudinal components which change sign above and below the beam axis, because the sign of the gradient of our field changes above and below the beam axis. And again, there is a 90-degree phase shift between the two components, thus giving rise to elliptical polarization and thus transverse spin, which changes sign as a function of transverse position. Okay, and also here we have spin momentum locking of light, meaning that if I now consider the situation where I reverse the direction of propagation, then of course the sense of rotation of my electric field will also change, meaning that the transverse spin also flips sign with the direction of propagation. And now let us consider that we are coupling an emitter, or we are driving, for example, or collecting fluorescence of an emitter, which is circularly polarized with respect to a quantization axis that points into the screen. Okay, so we're driving a sigma plus polarized transition of an emitter with respect to a transverse quantization axis, such that the dipole turns counterclockwise in the plane of the screen. Okay, and now let me ask, what should we do in order to collect fluorescence from this emitter and have the highest possible collection efficiency for a given numerical aperture of our collection optics? Okay, and of course our collection optics consists of some collection lens and some photodetector or CCD array here. And then naively one would say, well, you should place your emitter onto your beam axis, because there we have the highest intensity of the mode defined by our imaging optics, and thus the highest probability of collecting photons that are emitted from the emitter. And of course, if we now consider placing an emitter also circularly polarized on this beam axis, indeed half of the photons will be or the same amount of photons that arrive on our detector will also be emitted away from this detector. However, let us now assume that we move our detection optics somewhat downwards. okay? In this case, of course, the mode decreases in intensity, but at the same time, the polarization state of the mode that collects the optics here becomes slightly elliptical and better matches the polarization of my emitter. And this means that when I move my detection optics downwards, I will actually collect more photons on my photodetector at the expense of having less photons emitted to the left. So this is the same kind of chiral coupling that we observed for our nanophotonic waveguide, but this time in free space. And actually what this implies is that rather than picturing our fluorescing emitter like we usually do when it's circularly polarized here, as like some billiard ball that emits wavy arrows that issue from the emitter, actually for such a circularly polarized emitter, we should rather sketch it like this, okay? So the photons are actually emitted from a position away from the emitter, such that when the emitter is off the optical axis, the photons come from the optical axis and have the highest probability of being collected here. And this effect has actually been predicted already 88 years ago by Charles W. Darwin, who was considering the just classical problem of an electron that goes around in a circle and that radiates dipole radiation. And he actually noticed that the wave front of the emitted radiation does not face exactly away from the origin, but actually from a point about a wavelength away from it. And this implies, as I was sketching in this picture, that the photon, which is to carry away the energy and angular momentum of an atom, which is 10 to the minus 8 centimeters in diameter, actually starts its life outside of the atom at a distance of 10 to the minus 5 centimeters away from it. Okay, and let us see if that can be observed. For this, we teamed up with Rainer Blatt and his co-workers and actually determined the apparent position of a barium ion that was confined in a linear Paul trap, okay? And now we want to make the barium ion emit circularly polarized light with respect to a transverse quantization axis, which is defined by this magnetic field here. And in this case, it's not so easy because it's a J equals 1/2 to 1/2 transition. And basically you have to prepare the atom, say, in the MJ equals minus 1/2 transition. And then on average, you get one circularly polarized photon out, but then you also pump it to the other level. And this pi polarized light here it has to be filtered out in order to only see circularly polarized light. This is why we have this polarizing beam splitter. And then in addition, it's possible for the barium ion to decay to this 5D state here and emit light at another wavelength, which is also filtered out by this band pass filter here, okay? But then actually averaging for a long time, it's possible to collect a large number of sigma minus or sigma plus polarized photons, okay? And the transition on which we collect light has a wavelength of 493 nanometers. And the prediction for the apparent offset of the position of the barium ion between the two polarizations, sigma plus and sigma minus, is actually that wavelength, 493 nanometers divided by pi. So we expect an offset of 157 nanometers between the two images of the ion. So this is a small number when it comes to imaging, but it turns out that point spread function fitting does allow us to determine the position of the ion to much better than that, actually to a precision at the nanometer level. By just recording the image on our CCD camera and then fitting our point spread function to the CCD image. And then comparing the situation where the photons are sigma minus polarized and sigma plus polarized, we indeed find an offset of 158 nanometers, which nicely corresponds to this 157 nanometers, which is theoretically predicted. And while this is hard to see with optics, I would like to also stress that this offset that we see here between the two apparent positions of our barium ion is 1,000 times larger than the radius of the barium ion itself. So in that sense, I think it is justified to claim that here we are seeing a single atom where it is not. And just to explain what this actually means, let us assume that now in Rainer Blatt's group, they had, for example, some electron gun and they would like to shoot their ion, okay? So, and they want to shoot it by using a visor that just sees the fluorescence light from the ion. And then you would actually have to do the same as what you have to do when you are bow fishing. So you have to actually aim at a position which differs from the apparent position because the actual ion is at a different position than its apparent image. And this means that you just have to aim low to hit the ion, okay? So with this, maybe I have my break here and then ask for the first set of questions. So I don't hear you, Christian.
Now you hear me?
Yes.
Yes, okay. So again, thanks for the first part. And there are some questions. 4 from Bill Phillips. So I think I read at least 2 of them and give the others also a chance. So the first one is, you emphasized that for nanophotonics, you need a full vector treatment, certainly. But are there other approximations that must be abandoned for nanophotonics?
Other approximations. So I would rather say that showing the results with the ion, you see that under certain conditions, you even have to abandon the approximations that you use for bulk optics. Because what we see here for the ion is a breakdown in the sense of the paraxial approximation, a fundamental breakdown. This is an effect which is not there in the paraxial approximation. So I would say that what approximations do we do in nanophotonics? I think none, maybe. That when it comes to the electric field, and I would rather say that these results then make us look back to the bulk optics and see that we have to be careful there.
Okay, thanks. Another one is, for the directional emission, it seems that there should be something that breaks time reversal symmetry, perhaps something that looks like a magnetic field.
Yes.
Is that right? And also presumably there's plenty of emission into free space and not into the nanofiber. Does that change anything? So it's 2 questions in one, right? Yes.
Yeah. So first of all, it's actually the spin of the atom that breaks time reversal symmetry when we look at the atomic emission. So if I prepare an atom in this outermost Zeeman substate MF equals +5 and I reverse time, it becomes -5. So it turns out that there is, in that experiment, if I just look at the emission of an atom which is polarized, spin polarized, you don't need a magnetic field for breaking time reversal symmetry because the spin transforms like a magnetic field in itself. Okay. And then the question about emission into free space. Actually, yes, the largest part of the light is emitted into free space. And you could wonder whether if you take the total emission, maybe the directionality is again 0, right? But it turns out that no. So actually, even if I take the total emission into account, I get some predominant emission into one direction, meaning that actually an atom that is excited and decays near some dielectric surface actually feels a force that is parallel to the surface. Okay, so the recoil has a component that is parallel to the surface on average.
Okay, and maybe one more quick one by Jonathan Kuhn-Newman, and that was the question of the directionality, the maximum directionality that you observed in the gold nanoparticle and in the cesium cases was 40:1 and 10:1. Are these multi-level effects still, or the fact that you have many cesium atoms sitting on the fiber, or what is it?
So it turns out that directionality that we observed for cesium was larger than we would have expected theoretically naively in the beginning. And the reason is that our the nanophotonic field, or the evanescent field of the nanofiber, is not perfectly circularly polarized. And it turns out that if it's elliptically polarized, then naively one would say then you cannot have perfect directional emission. But it turns out that this is not true, and that if you choose your polarization to be orthogonal to the polarization of the left propagating mode, then in principle there's no limit to the directionality and can be unity. And since for the nanoparticle we were turning a wave plate and we're going through also elliptical polarizations, it turned out that we could have a better directionality than for the cesium atom, because the cesium atom really emits circularly polarized light, because we have a quantization axis normal to the waveguide, and we have a delta MF equals -1 transition in the emission. Yeah.
Okay, good. I think we should not break too long your talk into parts, so let's go on, and I ask the rest towards the end.
Okay, so then let me come to the second part of the talk, and I actually also changed gears somewhat, because here we will now look at the interaction of an ensemble of atoms with light that goes through the nanofiber. And this work has been done by PhD students Jakob Hinay and Ardash Prasad, and was supervised by Philipp Schneeweiss and Jürgen Volz. But there was also a very fruitful theoretical collaboration with Clemens Hammerer and Sahand Mahmoodian from the University of Hanover, and Anders Sørensen from the University of Copenhagen. So this part of the talk is about realizing strong photon-photon interactions, and there's a short introduction. I guess we all know that such strong photon-photon interactions are key to quantum information processing, because there you want to have some logical operation between the states, say, of two photons. And it's also key to quantum simulation, because you may want to have photons in some nonlinear medium interact and, for example, repel each other. And if the interaction is then large enough, you could have some kind of crystallization of photons where when you look at the correlation function, the intensity correlation function, it just vanishes for 0 time delay between the detection of photons, because they minimize their overlap. Okay, and usually for realizing such a strong photon-photon interaction, one harvests the strong nonlinear response of single quantum emitters that are strongly coupled to the mode that under study here. And that can, for example, be done in cavity quantum electrodynamics or waveguide quantum electrodynamics. But it turns out that in these schemes where you rely on a single emitter and its quantum nonlinearity, or an array of single emitters, dissipation is problematic, because it leads to photon loss and thus blurs out the nonlinear effects. And the essence of what I will be showing you is some approach towards such a problem, which is, if you cannot beat dissipation, then make it your friend. So if you cannot beat it, join it. Okay. So for that, let me come back to our nanophotonic waveguide interface for atoms. And here I will explain a bit more in detail how we actually trap atoms along the waveguide. This is done by sending simultaneously red and blue detuned light through the fiber, and the dipole force is exerted by the trapping light, and also their interference then gives rise to two diametric arrays of trapping minima. So here I sketched the optical potential for cesium atoms, 40 microkelvin and 125 microkelvin above the trapping minimum, and they are actually above and below the waveguide. And the confinement in these optical micropotentials is strong enough to allow for only one atom to enter the trap, because of the so-called collisional blockade effect. And at the same time, this collisional blockade then also limits the filling factor of to 0.5, meaning that we have at most one atom, and either 0 or 1 with 50% probability. The distance of the trapping minima from the fiber are around 200 to 250 nanometers, and the trap frequencies are in the 100 kilohertz range, and the atoms are localized in all 3 dimensions to much better than lambda, meaning that we are in the Lamb-Dicke regime. And there is a number of other groups that operate such nanophotonic atom waveguide interfaces here. So if you now send light through this fiber and load atoms into this trap, then if it's resonant light, via its evanescent field, it will couple to the atoms outside of the waveguide, and the atoms will scatter light out of the waveguide, meaning that the transmission through the waveguide is given or described by some optical depth, which is the negative logarithm of the transmission, where this total optical depth would be given by the optical depth of one atom multiplied by the number of atoms. And the optical depth of one atom typically lies in the range of 1 to 10%, whereas the number of trapped atoms in our nanofiber-based traps, or in nanofiber-based traps in general, is on the order of 1,000 to 10,000 maybe. So that means that the total optical depth would then be just the number of atoms times the optical depth per atom, and that ranges then from, say, 10 to 1,000. And of course, by writing this here, so saying that the total optical depth is the number of atoms times the optical depth per atom, I assume actually that the total transmission past n atoms is given by the transmission past one atom to the power of the number of atoms. And this is just Lambert-Beer's law that I assume here, right? And then when you actually look at the transmission as a function of laser detuning, so here I plot transmission and laser detuning in megahertz, and the blue dots are experimental data. You see that indeed we reach a completely optically dense ensemble of atoms, where over a frequency range of 30 megahertz, the transmission almost vanishes, and the red line is a saturated, or is a saturated Lorentzian absorption profile, which nicely describes this behavior here. Okay, and if you have seen me give talks about this topic here, then you probably have heard me say things like, here we have an optical depth of 32, which is extracted from this Lorentzian fit here, and an optical depth of 32 means that the transmission at resonance is only e to the minus 32. So I have been saying that for about a decade. And then came a paper by Sahand Mahmoodian et al., which actually considered the transport of photons through such a waveguide with weakly coupled emitters along it, and predicted that there are actually effects that we did not have on the radar at all. Okay. And then we got excited and wanted to study these predictions. And for that, we just trapped atoms along our nanofiber. Actually, I should say that the nanofiber in our case is realized as the waist of a tapered optical fiber. So this is a standard step index fiber, which is narrowed down to sub-wavelength diameter. We trap atoms along the fiber, and then we send probe light, which is resonant with the cesium D2 line, into our tapered fiber, and now look at the light that is transmitted past the atoms. And here the input power of this probe light is actually only 2 picowatts. So that means that the intensity at the position of the atoms corresponds to a saturation parameter of only 0.02. So this is really very weakly, in the very weak saturation regime, and you would probably expect some linear response of your atoms to this light field. And just to mention that this probe light was quasi-linearly polarized, meaning that this chiral light matter coupling did take place, meaning that the atoms absorb light from the left and emit it to the right, but this was not essential for the outcome of this experiment, actually. So now let us look in detail at the microscopic processes that take place when photons now travel through this waveguide and couple to the atoms one after the other. Okay, so for this, we have to briefly revise resonance fluorescence, because the atoms are excited and then fluoresce. Okay, and we know from resonance fluorescence that if the saturation is vanishing, then atoms arrive one by one at the atoms, and thus the energy has to be conserved, and the scattered photons have exactly the same spectrum as the laser that is excited the atoms. And we refer to this as elastic scattering. So the spectrum of the scattered light is just a carbon copy of the laser spectrum. However, we never have vanishing saturation, so meaning that there's always some finite probability for two photons being at the atom at the same time. And in this case, actually, it's possible to have such a 4-photon process happening. So 2 pump photons arrive at the atom within the lifetime of the excited state, meaning that the 2 emitted photons can now differ in frequency or energy from the pump photons. And it's just the only condition is that in total, energy has to be conserved. That means that the sum of the energies of this red and blue photons has to be equal to 2 times the pump photon energy, okay? And this means that now the fluorescence actually can have spectral components that differ from the laser. And in addition to this elastic component, we now have the so-called inelastic background, which has width here, spectral width, which is given by the line width of our excited state here, okay? And I would like to stress that while we usually just say that this background here is incoherent emission, it actually corresponds to correlated photon pairs, because these photons are simultaneously or in close temporal succession emitted, and they are correlated in energy, meaning that their sum has to be equal to 2 times the pump frequency. And now let us look at what happens if such emitters, with taking into account this possible nonlinearity, actually interact with the light in the nanofiber. And we now only consider the 2-photon component. And our laser emits initially a spectrum which is very narrow, say a delta function, and we now look at the 2-photon component contained in this laser field, okay? So then this 2-photon component can undergo 2 processes when it encounters an atom along the waveguide. It can either, one photon can be scattered out of the waveguide, or they can be just transmitted past the atom without interacting, or this nonlinear process takes place, and we have a correlated pair of photons emitted by the atoms, okay? So the 2-photon scattering generates this correlated 2-photon state, but this correlated 2-photon state has a broader spectrum than the laser, the initial laser field, which means that it experiences reduced absorption by the rest of the ensemble. So the following atoms have less chance of absorbing the correlated photon pairs than the 2-photon component from the laser. In addition, there is constructive interference taking place in this 2-photon scattering process, because here it's forward scattering of the 2-photon component, and all the amplitudes coming from each of these atoms here constructively interfere, okay? So this means that this constructive interference leads to a collectively enhanced 2-photon forward scattering process. Okay, so all the atoms interfere constructively. At the same time, the unscattered component is, of course, subject to exponential loss because at each atom you have some probability of removing 1 photon from our pump photon pair. And this means that we actually have now the unscattered 2-photon components is subject to exponential loss. So this is what I said. And this means that we now have a power law decay of the correlated photon states with the number of atoms. So this is really surprising. The correlated photon pairs, which have a broader spectrum, actually experience absorption, which scales polynomially with the number of atoms rather than exponentially because of its broader spectrum. Okay, so if we look at the spectrum of the light that then exits our waveguide after interacting with a number of atoms, it will have a strongly suppressed pump wavelength here. And we will have this incoherent background, which is collectively enhanced and filtered by the absorption of the atoms. So this dip here comes from the atoms absorbing the correlated photon pairs, but you see that out here, we still have a lot of correlated photon pairs that were not absorbed by the atom, okay? And now there is another important aspect, which is that this two photon component, as indicated by the phase of these waves here, is actually pi phase shifted with respect to the unscattered two photon component. And this means that the correlated component here interferes destructively with the pump light, okay? And this destructive interference then leads to a modification of the probability of having two photons at the same time in the waveguide. So if the scattered amplitude is smaller than the unscattered component, and that happens for low optical depth, then we expect that there is some anti-bunching taking place. So in the beginning, laser light has just a flat G2, but then the interference of the scattered component with the unscattered component reduces the probability of finding two photons at the same time, and we see some slight anti-bunching. And if we further propagate the light along the waveguide, then at some point, the amplitude of the scattered and unscattered two photon components will be equal, however, with opposite sign. And this means that they actually interfere perfectly destructively, and we expect perfect anti-bunching. And if we further propagate the light, then there's only the scattered two photon component which survives, and we expect strong bunching. Okay. So we did this experiment. We looked at the photon statistics of the light as a function of the number of atoms. And here is actually the experimental data and the theoretical prediction. So for 100 atoms, for 160 atoms, 180 and 200 atoms. And you see that indeed we go from slight anti-bunching to stronger anti-bunching or maximum anti-bunching for 160 atoms to the onset of bunching and to strong bunching. Mind that here the scale of the vertical axis changed. While it goes to 2 here, it goes to 10 here. So we have here significant bunching for this high optical depth. So the blue line is the experimental data, and just to convert the atom numbers here into ODs, they range actually from 3 to about 7 for the highest ODs here. And this orange line is the theory prediction for our experimental parameters, which takes the experimental imperfections into account. And the largest experimental imperfection is actually a variation in the atom number distribution. So actually we have on average 180 atoms here, but we cannot determine it and prepare it precisely. And so there's some smearing out of the atom number. The atom waveguide coupling strength was about 1%, and we extracted that from fitting the value of G2 at 0 time delay with only the coupling strength as a fit parameter. And let me show that fit to you. So here we show the the G2 at 0 time delay as a function of OD. And you see that indeed we have a strong anti-bunching up to an OD of about 5. And the orange line is again the theory prediction that accounts for our experimental uncertainty, and that has the coupling strength of the atoms to the waveguide as our fit parameter. And just for comparison, the green dashed line here is the theory prediction without the uncertainty in the atom number. And you see that then indeed you expect perfect anti-bunching for this optical depth of 6. Okay, so the strongest anti-bunching is observed for 160 atoms. This is this data point here. And actually we start to see bunching from 180 atoms onwards. And to actually show you this data, I changed from a linear scale for G2 to a log scale. And then you see that for the high ODs here up to 8, we observe a G2 of tau equals 0 of about 20. So very strong bunching. So this showed that an ensemble of weakly coupled atoms can actually be useful to realize such strongly correlated many-body states of photons, where we change the photon statistics due to some collectively enhanced nonlinearity. So the underlying dynamics is really some interplay of a weak optical nonlinearity of each atom, which, however, interferes constructively such that it's collectively enhanced. And we also need the dissipation in this process in order to suppress the pump light exponentially along our waveguide. And as perspectives, I would like to highlight that these results actually show you that you can extend the use of collective enhancement, which has been used a lot for atomic ensembles, for example, to enhance the coupling strength of the atoms to the waveguide. This collective enhancement can also be used for this nonlinearity and thus extend this use of collective enhancement to non-Gaussian operations. And this means that we now have like a new toolbox which can like broaden the range of applications, for example, in quantum information processing. And here, as just to name one example, we think that this process allows us to have a fundamentally new approach towards realizing single photon sources that can be, in the case where you do not have a single strongly coupled emitter available, say for a certain wavelength range, actually be much brighter than a single emitter of the same coupling strength. And with this, actually, I would like to thank the funding agencies that supported this work. And I thank you for your attention, and I'm looking forward to the questions for the next part.
Yes, Arno. So let me first thank you for the talk and pass over some questions. There are quite many, actually. So let me first start with questions to the first part of your talk that I couldn't really read in the middle. So one by Gabi Slavcheva is, have you looked at the directionality of second order coherence in the, well, regarding the first part of your talk? Does it exhibit bunching or anti-bunching?
So I assume here that, I mean, we did, so first of all, we did not do a G2 analysis of the light emitted into the nanofiber. I should say that here it was an ensemble of atoms. Okay, when I mean, it's only interesting when we talk about atoms, I guess. And this experiment was carried out with a few 10 atoms. That means that I think that the statistics of the light emitted by this ensemble is not modified by the directionality. It's just the chiral coupling comes from a density of modes that you offer to the atom, which is asymmetric concerning the direction of propagation in the waveguide, but it does not alter the fundamental processes of emission into the waveguide, in the sense that the photon statistics, I expect different photon statistics than for emission, for non-chiral emission.
Okay, then we have two questions basically. Still the first part in the story, seeing the atom where it's not. So Bill Phillips asked, you compared the physical size of the atom to basically the shift that you saw optically, right? So now, but what about the size of the wave function of the atom?
Yeah, well, I mean, the physical size in the sense is given by the size of the wave function, but of course you still have some exponentially decaying probability of finding the electron out there. But I don't think that it is this smearing out of the electron wave function, which has a small probability of being out there. I mean, we're talking about 1,000 Bohr radii, okay? I would rather say that when considering the atom as a radiating object, then I have to also look at the size of the near field of the radiation that is emitted. And in that sense, the size or the distance of the apparent origin of the radiation coming from the atom is precisely the size of this near field. So in that sense, I would say that we are seeing the atom where it is not, if you consider it in its ground state, but once it is excited and radiating, then it also, I would say the near field is part of the atom, and then you could say that it is larger. But that doesn't mean that it's the wave function of the electron, but rather the excited atom plus the radiation maybe.
And but maybe just to complete the picture of the sizes, how big is the center of mass wave function in the ion trap?
Oh, I would have to ask Rainer Blatt, but typically, I mean, for the trapping frequencies they have are much larger than for our traps, and we have some tens of nanometers of size in our optical traps. So I assume that it's a few nanometer wave function. I don't have the precise number, but given the megahertz oscillation frequencies, it should be less than or on the order of 10 nanometers, I guess.
Okay.
So still much smaller than the apparent shift.
Yes, so I interpreted actually right. Bill is saying on email that was basically his question, the last part. Good. Okay. Another question regarding this by Ofer actually, and he asks, if you draw this picture of the bowfishing, shouldn't the arrow itself not also refract somewhat when it enters the water?
Well, I'm not a bowfisher, but my understanding was that the arrow goes pretty much on a straight line and is not deviating from its initial trajectory. I mean, this example of bowfishing, I mean, I showed that because it's funny, but of course there is an important difference between what we have here for the ion and the bowfishing, because for the bowfishing, you do have a dielectric interface. And so there is clearly something that changes the apparent position, right? But for the ion, you look at the ion in free space, and there's no such thing as a dielectric interface that changes the apparent position. Okay, so in that sense, it is because of this, if you like, chiral coupling, or you can also find different pictures that explain it, angular momentum conservation, etc. But I think that it's even, I mean, for the bowfishing, it's kind of obvious, whereas here you would not expect the ion to be at a different position because you just use bulk optics to image an ion.
Okay, so then let's come to the second part. So first about how you generate those traps for the cesium atom. So there was the question, when you say the minima are above and or below the waveguide,
yes,
is that because of the linear polarization of the light in the nanofiber? And
yes,
if yes, could you turn that polarization and with that move the traps? And yes, then one step even further. Now, if you rotate the polarization quickly, could you generate actually toroidal traps?
So you don't even need to. So maybe I have some. I mean, I do have some slides here on the realization of the nanofiber-based trap. Thanks for the question. So actually, as I said, we launch red and blue detuned light with respect to the D2 transition of cesium into the nanofiber, and then the red light polarizes the atom in such a way that it is attracted by the high intensity regions, whereas the blue light repels the atoms from the high intensity regions. And when an atom approaches the fiber from a distance, it will, because of the different decay lengths of the red and blue detuned field, first feel the attractive action of the red field. So here's, I plot the potential energy of the atom as a function of distance from the fiber, and the red potential is attractive and it reaches out further into the space around the fiber. And when the atom approaches the fiber further, it starts to feel the repulsion from the blue, and the black line is the sum of the two potentials, the repulsive and attractive. And you see that there is this radial trapping minimum about 200 nanometers from the fiber. And then the question was, why is it azimuthally confined? First of all, axially, we confine it by launching the red light from both sides. So we create a standing wave of the red light. So the attractive potential is modulated along the waveguide. And then if you look at this picture, you would already say, well, there's a cylindrical waveguide, which means that if I now confine the atoms in the radial and in the axial direction, I do have toroidal traps. Okay, so the first assumption would be here, I do have toroidal traps. And then indeed what breaks the azimuthal symmetry and spoils the toroidal traps is the linear polarization of the trapping light fields, which we use actually to confine the atoms in the azimuth direction. Because it turns out that in these strongly guiding waveguides where you have a strong index of refraction jump, I do have to consider the vector properties of the light. And it turns out that in the plane of linear polarization, I have 3 times more evanescent field intensity than orthogonal to it. So that means that if we launched red and blue detuned light fields with crossed linear polarization, I have more attractive light here and more repulsive light here. And thus I have 0D traps. But now let us assume that we send the blue and red detuned light just circularly polarized. In this case, nothing breaks the azimuthal symmetry, and we do indeed have toroidal traps. So we can and did realize toroidal traps, and we don't have to rotate the linear polarization fast for that, but we just use in the first place, circular polarization for the red and blue light fields, and thereby do not break the azimuthal symmetry and generate toroidal traps.
Okay, good. So maybe one more question that is pressing and was asked in similar manner by 2 people. And that is about the connection of your correlated frequency shifted photon pairs to the Mollow triplet. So that would be a first part. So how is that connected? And the second thing is also from Bill, for multi-level atoms, there's another broadening mechanism that, if he remembers correctly, predates Mollow. This gives a width related to the excitation rate, not the spontaneous rate. Did you take this into account?
So the first question was, what is the relation between the spectrum that I showed and the Mollow triplet? So let me go back here. Actually, this is the Mollow triplet in the unresolved sideband regime, if you like, because we have weak saturation, meaning that the Rabi frequency is much smaller than the line width of the excited state, okay? And thus we have just this elastic peak plus this incoherent background, which can be seen as the 2 sidebands of the Mollow triplet that overlap, okay? So when you further increase the Rabi frequency, then this becomes broader and then moves outwards. And you do indeed get the sidebands from the Mollow triplet. And also in the Mollow triplet, you have these correlations between the red and blue photons. Okay, so this has been observed because it's about 2 photons arriving at the same time, and it's a nonlinear 4-wave process, but energy has to be conserved, meaning that if I see a red photon, afterwards, I can only have a carrier photon or a blue photon, but not again a red photon. So these correlations are also there when you go to this higher saturation situation where the Mollow triplet really exhibits 2 sidebands. Yeah. And also the space, there's some temporal order between the emission of the photons in the Mollow triplets, which also is given here, right? So if there is a red photon, then the blue photon must come immediately or within the lifetime of the excited state. And then the second question was a broadening mechanism for multi-level atoms that predates Mollow. Sorry, Bill, that I'm not aware of that effect, and thus we did not take that into account, or let's say our theory co-workers did not take it into account neither. Yeah. You have to maybe send me an email to enlighten me about that, but I was not aware. Actually, but I should also stress, but maybe that saves me or my ignorance, that here we prepare the atoms, well, automatically in our experiments, the atoms are prepared in the outermost Zeeman substate, and we are scattering light on a cycling transition. Okay, so that means that the atoms are to a very good approximation, two-level atoms, and the physics is actually about two-level atom physics.
Okay, I think time is pretty much over. There are 2-3 more questions that we will send you then basically by email. And let me thank you again for the really great talk, very pedagogical, and yeah, not much to say. Thanks. I can try to clap in behalf of all the others.
Thank you very much.
And I give the word then back to Sebastian, I think.
Yeah, thank you very much, Christian. And also Arno, again, thanks for a great talk. This was really cool. And I'd like to remind you that next week we will have another talk, and this is your only chance in the next week, I guess, to have Bill Phillips answering your questions, because Bill Phillips will be giving a talk about the quantum reform of the SI system. And you should certainly attend that and ask all the questions you can think of. If you want to get notified of what else is going on, please go to our website, quantumscienceseminar.com, where you can subscribe to our email list, to our Google Calendar, and you can now even follow us on Twitter. Please check out our sister seminar, the AMO seminar, which is on hiatus this week, so no talk tomorrow, but next week they will have Dave DeMille speaking. And with this, I'd like to thank you for your interest, and we hope to see you again next week.